All right. Unit 8, subsection 2, antiderivatives as an area, part 2, finding the area between two curves. Okay, so last section we figured out the area between the graph and the x-axis. So now what if there's two graphs or two lines and we want to figure out the area between them? Okay, so I've drawn a little picture here for you. So there's a graph, a curve, and then a straight line, and we want to figure out those two areas. Okay, so there's two methods to do these. Okay, and I like method 2 better because it's just less math, but you guys can choose. The idea is, method 1, find the area under each curve for the given interval and then subtract. So if we use last section's method, okay, we figure out the area under this curve, okay, all the way to the x-axis. Okay, great, that would give us a number. And then we do the same thing for, here I'll write in red now. Then you do the same thing for this guy. Okay, and then subtract the two areas. So you take that guy and subtract him. So it works, but you have to figure out two integrals, and it's just a lot. Okay. The second method, which I like to use, but again, it's up to you. So we write a single function that has the top function minus the lower function. Okay? Then we find the area between them by finding the area under that curve, or the area under the curve of the new function between the x-axis and the function for that given interval. Okay? It's pretty straightforward. Because each of these methods uses a variation of the top function minus the bottom function, a similar issue arises like it did last section. What happens when the functions cross each other so that both curves are on top for a portion of the desired boundaries? Okay, so just like last time, we have to evaluate the different regions where each function is on top and add the results. Okay, drawing a sketch or graphing the functions on your calculator will be a very handy skill, and example 3 will demonstrate that part of it. All right, so let's get on with it and see where we go. Okay, so example 1. Find the area between the curves y equals x squared plus 2 and y equals x from x equals 1 to x equals 3. Okay, and we're going to start by sketching the two functions. Okay, I showed this first one for you just so we can go. All right, notice that the squared one, the x squared plus 2, is always on top, or at least for the interval that we want. Okay, so that is going to be the top function. The y equals x, that's going to be the bottom function. Okay. Awesome. So we're going to go over here. So top minus bottom. Okay, so the top function is x squared plus 2 minus x. Okay, easy enough. So let's do a little bit of rearranging. So that's going to be x squared minus x plus 2. So this is our new function. So if I take the integral of that down to the x-axis, that's going to give us the same area as evaluating both of them and then subtracting. Exactly the same thing, so you can do it that way if you really want, but I think this one is easier because you only have to do one integral. So the integral from 1 to 3 of x squared minus x plus 2 dx. Awesome. Okay, so again, taking the integral of this, that's going to be x cubed times the reciprocal, so 1/3. So let's put the 1/3 out here. Okay, minus, that's going to be x squared, okay, times a half, so let's put the half in front, and then plus 2x. Okay, and I need that from 1 up to 3. Okay, again, don't be martyrs, just type this into your calculator. Okay, and you end up with, alright, so 3 cubed is 27 times a third is 9. Sorry, too much work. Just type it in. So that is 21 over 2 for the 3. And then we're subtracting, so for the 1, That's going to be 11 over 6. Okay, not a big deal, which of course, when you subtract that, is 26 over 3 units squared. Awesome. Okay, so again, I think the easiest way is to subtract the two functions, top minus bottom, and then take that one full integral, and I think that's easier. Okay, number 2. Find the area of the region bounded by the parabolas y equals x squared and y equals 2x minus x squared. Okay, so we have to do a quick sketch of this again. Okay, so x squared just looks like this. Okay, and then 2x minus x squared. Okay, so that guy has zeros at x. Oops. 2 minus x. Okay, so that guy has got zeros at 0 and at 2. So it goes like this. All right, so what this question is asking is it wants this region here. Well, that means we have to figure out that point up there as well, because we know that intersects at 0, 0, so that's fine, but we also need to know that one. So how we do this, at least algebraically, is, oh look, the two equations are both y's, so that means that x squared equals 2x minus x squared. Okay, awesome. So let's see, let's move that guy across. So that's going to be 2x squared equals 2x. Okay, easy enough. I guess we could factor, but we could also bring that over. So 2x squared minus 2x equals 0. So we take the 2x out, and you're left with x minus 1. So they intersect at x equals 0 and x equals positive 1. Really what this tells us, the interval is from 0 to 1 is what we want. Okay, now the other thing we notice from this is that the 2 minus x squared is always on top. For the region we want, it's always on top. And then y equals x squared is always on the bottom. So when we go top minus bottom, okay, we get 2x minus x squared minus x squared. So that equals 2x minus 2x squared. Okay, so that's the function that we want. Okay, so we're going to take the integral from 0 to 1 of 2x minus 2x squared. Awesome. dx. Okay, so the integral then, so that's going to be x squared times 1/2. Well, that 1/2 is going to cancel off with the 2, so it's just x squared. Okay, so again, notice I'm not going to write the 2 anymore. I'm just going to go write the x cubed. Okay, and that's going to be times 1/3. So then that's going to multiply the 2, so that's going to be 2/3. Okay, and we can just do it kind of in a smaller step. Okay, and that is evaluated from 0 to 1. Okay, so multiplying all this in, we get, so 1 squared is 1, 1 cubed is 1, so 1 times 2/3 is 2/3, so 1 minus 2/3 is just 1/3. Okay, so that's going to be 1/3 units. And then, if I put a 0 into that, that's just going to be minus 0. So this is just 1/3 units squared. Okay, and that is the area between the two curves. Okay, and last one, everybody. Okay, so find the area of the region between the curves sine x and cosine x for x equals 0 to x equals pi over 2. Wow, that's going to be a tricky one. So we need to reach back from our trig unit in Math 31 and the trig unit in Math 30-1. Remember, sine x looks like this. Okay, starting at 0, 0 and going forward. So then Okay, so this guy here, that is at pi. Okay, and then okay, so this top part's going to be at pi over 2. Okay, now cosine starts at the top and goes downward. Okay, like so. All right, so the region we want is from pi over 2 to 0. Oh, and if you look at this, look, the graphs kind of crisscross here. So cosine is on top for this first bit, and sine is on top for the second bit. So we need to know where that point is. Now, you guys are pretty smart. Intuitively, that should be pi over 4, right? Where sine x equals cos x, but we should prove it. So when we do this, we go sine x equals cos x. Okay, so a nice little trick here is to divide by cos x, Okay, now you'll remember that sine x over cos x is tangent x, and cos x divided by cos x is 1. So, tan x is 1. Well, that's 1 over 1. That's opposite and adjacent. Okay, so either for the unit circle or the special triangles. Okay, if the opposite is 1, the adjacent is 1, that's the root 2. So that's the 45 degrees or pi over 4 triangle. So x equals pi over 4. Okay, fantastic. So really, I want, there's going to be 2 spots here, or 2 intervals. So cos x is on top here. So for the first part, it's going to be cos x minus sine x, because cos x is on top, sine x is on the bottom. For the second part, sine x is on top, so it's going to be sine x minus cos x. Awesome. Now, please, once again, these 2 areas, they're going to be symmetrical, aren't they? Sure they are. So really, if we just find the first one and then times this by 2, we're going to get it. But again, for the sake of the example, we're going to do it both ways and just add them, and we'll see that part in the end. Okay, so I'm going to take the integral of cos x minus sine x, okay, of course dx, okay, and we're going to do that part from 0 to pi over 4. Okay, and the second part is going to be the integral from pi over 4 up to pi over 2 of sine x minus cos x dx. Okay, so again, I'm going to write my little stuff here. So the derivative of sine is cos. The derivative of cos is negative sine. So the integrals just go backwards. Okay, so the integral of cosine is sine x. So that's sine x. So the integral, oh look, it is negative sine. So the integral of negative sine is cos. So this is going to be plus cos x. And that is from 0 to pi over 4. Okay, so that's this part. So sine pi over 4 plus cos pi over 4. So pi over 4, look, I've already drawn the triangle. You can use the unit circle if you want. So sine of pi over 4 is opposite over hypotenuse. That's 1 over root 2, which is root 2 over 2. Cosine is exactly the same thing. So sine, so really that is just 2 root 2 over 2. 2 over 2, which of course cancels. So this whole thing is just root 2. Awesome. Okay, so this part is root 2. Okay, then of course we have to minus, okay, what happens when x is 0? Well, sine 0 is 0, and cosine of 0 is 1. So Sine 0, 0. Cos 0 is positive 1. So then you're going to get a negative 1, so root 2 minus 1. Okay, so that's that part. Okay, marvelous. Now, again, we could just multiply this by 2, and we'll get 2 root 2 minus 2. Okay, and so that's going to be our final area, units squared, because we know those two regions are symmetrical. But you know what, again, it's the example, so I do want to figure it out. So we take the integral of sine, so sine x would be negative cos x. Okay, and then minus the derivative of cos is sine x from pi over 4 up to pi over 2. Okay, great. So let's see, cos pi over 2 is 0, and 0 times negative is just 0. Okay, minus sine of pi over 2, well, that's just 1. Okay, so that's the first part, minus, so now pi over 4s. So cosine of pi over 4 is 1 over root 2, or root 2 over 2, then times the negative. So that's going to be negative root 2 over 2. And then sine pi over 4 is going to be root 2 over 2 again, but oh look, subtracting. So that's minus root 2 over 2. Okay, so that's going to be negative 1 minus negative root 2, right, because that's going to be negative 2 root 2 over 2. Yeah, do that. Negative 2 root 2 over 2, so the 2's cancel. Okay, so this is just going to be negative 1 minus minus, so plus root 2. Okay, great. And then, of course, we add that to those. So the 2 root 2's make 2 root 2. Negative 1 makes minus 2. So basically this whole part was unnecessary because we knew they were symmetrical from the start. But I still wanted to prove it to you guys. So again, we take the two regions, we add them together, and we get 2 root 2 minus 2 units squared. So again, when the top function and the bottom function overlap, okay, you have to figure out those regions again and take the two regions separately, add them together, go from there. So I know this is a little bit tricky, but this is also the end of areas, so yay. And please do the formative assessment. The summative assessment for this one is combined with the last section. So call me if you need anything. Talk to you later.